Mr. Ramji, my other friends from the Agastya Foundation, and my fellow teachers. Well, I am happy to be able to talk about a subject which some people may consider controversial, about science for science's sake. Should we be doing science for science's sake? I remember that the phrase art for art's sake used to be very common once upon a time. Science for science's sake was not. However, as we understand more about how science has developed, we begin to see the importance of people who work for science because they love it, because they have a passion for it. That's actually true not just for science, I think it's true for almost everything. Because the love for doing something, passion for doing something, means that you don't feel tired. If you have time, people who have passion are probably likely to spend most of their time pursuing whatever they actually love. If you look at the great scientists of the world, whether in India or outside, you think that passion is something that's common among them. You can go back to Newton, for example, or even the Greeks, or even our own great men like Aryabhatta and Brahmagupta and so on. They all have that thing in common. However, somebody from outside science, and there are several, there are even several who think science and technology is either a double-edged weapon or in fact even can ruin us and so on. They will say, well, you can keep on doing science, but what good is it? I mean, a lot of the science is done. What is it good for? It's the characteristic of some of the deepest science that's been learned by human beings over the millennia to seem at first absolutely useless. In fact, there was not long ago, just about a month or two ago, there was a very interesting lecture here in Bangalore on the usefulness of useless science. Now, you remember that about 100 years ago, almost exactly 100 years ago, Hardy, who was Ramanujan's guru and patron in Cambridge, at that time, certainly the greatest British mathematician, one of the greatest world's mathematicians. He wrote a little book about mathematics and why people do mathematics. And he said, thank God the mathematics I'm doing is useless. But he was wrong. It in fact became useful, although at that time it was not at all clear where it would be useful. So very often the things which we dismiss as useless have applications on problems which have not yet arisen, whose existence we have not yet seen. Well, as far as science is concerned, now making a little distinction from mathematics, the number of ideas in technology that have come out from science, basic science done by some crazy man who just loves to find out how things are happening and why, is very large. It's true that there was a time when whatever technology we had came just for trying out things to meet daily needs and other needs for survival. But as time went by, ideas seemed to get more abstract, and it was only after some experience that we began to see that science which seems useless today may turn out to be very useful tomorrow. So let me start with one well-known example. Take Einstein. When Einstein wrote that paper on relativity, that's around 1905 or so, and said, well, there's the speed of light. It is not true that mass is conserved. It is not true that length remains the same. Depending on how you move, or how the object moves in relation to wherever another object is, time and space can shrink, and mass can be converted to energy. Well, that was almost like blasphemy to many people. And they said, what are you saying? This is all nonsense. Many of you might have heard that in the time of Nazi Germany, well, even before actually they came to power, Einstein was criticized, and his ideas were said to be Jewish physics, publicly. and by people who are not by any means to be considered stupid. They said it just doesn't make any sense. It goes against every feeling we have. But if you look at what happened 10, 20 years later, one by one, the evidence accumulated. And by the 1930s, it was clear that relativity was right, and in fact, there was evidence for these changes that take place according to the theory of relativity. If the speed of the object is getting closer and closer to the speed of light, the speed of light in vacuum became a reference speed. And if you're getting closer there, all kinds of dynamics would happen, and that had nothing to do, had no resemblance to what you did out of Newtonian dynamics. Well, there was in the 1930s, it's interesting that the President of the United States appointed a commission of scientists, well-known scientists, to tell him what might be most important 10 years from then, in the mid-40s, say, mid or late 40s, 10 years from then. What is it? What is the science that might have emerged, and what should we be getting ready for? And these distinguished scientists looked at things in great detail across the whole span, from agriculture to physics and so on. And they all told the president how things would change. But the changes that they had in mind were all incremental. Well, this will be 50% bigger, that will be 100% bigger, so on and so forth. But by the 1940s, if you compare what had happened with what they had predicted, you would see that a revolution had occurred. Actually, two revolutions had occurred, at least two. One was nuclear energy. By the mid-40s, E equals mc squared was no longer doubted. In fact, that conversion of mass to energy was taking place on behalf of the US Armed Forces, led to the nuclear bombs which were thrown on Japan. But at the same time, it was also realized that you could actually make energy out of it, convert nuclear energy to ordinary energy, and you could get your power that way and so on. So it was clear that there were applications. It couldn't be called useless at all. But nobody could have imagined that that would happen in 1905, or even as late as 1920, when Einstein's ideas were seen as far away. Well, there are always people who say that any new science is useless, or maybe even threatening. But usually what new science does is sooner or later, sometimes maybe later, lead to new technology. Now this the technologists don't know till the science actually is clear and has been confirmed as at least at the best standards of that time true. Till that happens, of course this is not clear, but in general it actually usually finds application. Let me take another example. Just now, recently, we've heard about the LIGO project in physics. Now, that was an extraordinary project. It started somewhere around 1990, has been going on for nearly 30 years, run by Caltech and MIT, looking for gravitational waves. Well, I actually remember, I was a student at Caltech in the late 1950s and early 60s, and I remember the day when Feynman gave a lecture on gravitational waves. Are they there or are they not there? And those who have not heard Feynman, at least seen him, maybe on videos or whatever, have no idea what kind of a speaker he is. He is an extraordinary speaker, very informal, not like a serious scientist at all. I rarely saw him wear a tie and coat. Loved to speak to young people, and had an enormous sense of humor and great imagination. And so he was talking there about how things could be done in a variety of areas, and also about gravitational waves, and about whether they're quantized or not, etc., etc. I also heard him once talk about there's a lot of room at the bottom, which led eventually to nanotechnology. And he said it would happen. But at that time, I don't think people took it very seriously, but they all enjoyed the lecture. So, I don't know whether there's going to be any use for gravitational waves, but you can never tell. So, let's wait for some more time before it actually happens. When electromagnetic waves were discovered, there's that story which many of you might have heard. I think it was the Prince of Wales in England. I may be wrong there. I may have my memory is not absolutely reliable. Anyway, he was a royal somebody, and in one of these exhibitions, Faraday is there showing evidence for these electromagnetic waves, and he's asked, "What good is this?" Okay, it's very interesting. What good is this? He said, "Your Majesty," if that was the Queen or King, "Your Majesty, you will be taxing it before long." Okay, and he told them, you might make motors and so on. So that is the nature. That's the nature of science. When Maxwell discovered those equations, he was not going to do it because he would make money out of electric motors. He was doing it because it seemed to him extraordinary. And his equations had such beauty and such consistency that he was very clear that that's probably what the truth is. But it turned out not only that it was true, and that's what actually led to relativity, when a little quirk was found there about the speed of light. But it just shows how what happens in the future we can't really pinpoint, but in most cases they become actually very useful. Well, take the astronomy itself. Is astronomy of any use? Of course, those who believe in astrology will say, of course, it's extraordinary, it's a great, extraordinary use. Well, there are many people who don't believe in astrology, but whether you believe in astrology or not, apart from those who have a faith in astrology, is there any other use from astronomy? At first, once again, it looks as if you can't see what it was. But you do know, you can predict when eclipses occur. So the fear of eclipses, if they're unpredicted, might be very large. So that fear at least is removed. And the fact that it shows that eclipses can be predicted accurately, and especially in the 19th century, by the use in astronomy of the law of gravitation, which Newton had discovered, has a totally different and revolutionary effect on our knowledge. Because the thing about the law of gravitation was not that it was the special property of astronomical objects. It was that any piece of matter in this whole universe will attract any other piece of matter in this whole universe by only this relation, which depends only on the two masses and the distance between them, nothing else. It was the universal law of gravitation. That was actually the great discovery. And what it says is everything, the attraction between me and this, or Earth and the Moon, whatever, or the tides on the River Thames, which is what Newton showed, they all follow the same law. The universe is governed by universal laws. They're the same, no matter what the objects are, where they are, and so on. It was a big boost to universality. Newton himself found it difficult to believe that there was a universal law of gravitation. And in fact, he's very cautious about saying what it is. And he, of course, had a little tiff with the priests in Europe, and in particular in England. But I think he was internally convinced that it was universal because of the evidence that he presented. Well, let's come back to India. Now, what was the science that was known in India? What was the mathematics that was known in India? This is something that that has attracted the attention of several people. But at the same time, in today's India, in contemporary India, is a matter of very great debate. And that's because there are some people who say India's science was great. It will be found in the Vedas. Our ancients knew everything, including relativity and quantum mechanics and so on. It goes on like that. But there are others who will say, well, there was no science in India. Whatever science there is has come from Europe to us in the last 400 years. Maybe some from the Greeks about 2000 years ago. But really there is nothing in India that's worthwhile. Now I've looked at this question for a long time, and I've come to the conclusion that that's not true. My own view is that if you look at the history of science, there have been periods where some civilizations, some cultures have done very well, and other periods where they have not done so well. And India is an excellent example of that. I think till about, if you take mathematics for example, I think Indians have had a feel for numbers for a long time, going much earlier. But I am convinced that there was a mathematical revolution in India beginning around 500 AD. Let's say with Aryabhatta, around that time. I don't mean Aryabhatta himself, but around that time, things changed in India. There's no doubt about it. Because if you go back before Aryabhatta, it's not easy to find any text that talked about the things that he does. And that lasted till about 1500. For about 1000 years, mathematics in India bloomed. But what was this mathematics? If you ask the Europeans, they will say, well, mathematics started in Greece. But the mathematics in Greece was geometry. In fact, they didn't use the word mathematics. They used the word geometry. It's only later on that we began to interpret geometry also as mathematics. If you go to Plato's Academy, where it would have said, sometimes they say, anybody who does not know mathematics is not admitted here. It did not say mathematics, it said geometry. Okay? There was another part to mathematics. That other part was complementarily being discovered in India, namely algebra, handling numbers, handling equations, handling unknowns. These are all actually very Indian. They're not European. And the equations, the first equations were written down in India in a notation which we can still understand. It's not quite the same as what it is today in algebra, correct contemporary algebra, but you can see how one thing could have led to another. It's only around 1500, 1400 that the Europeans began to discover algebra. Because algebra, Bijganita as we called it, went from India to the Islamic lands. There have been empires which have had parts of Persia and so on, and parts of India in the same empire. So there was a lot of communication. And that was obviously very different in character. And it began slowly to make impression on the Europeans. And as its strength began to be seen, they were confused. They had been raised on the belief that whatever was scientific came from the Greeks, or mathematical, or geometry as they would have said. And they could say, how could the Greeks not have known algebra? It's not true that it can come from the East. All of us have heard of Descartes. Descartes had, over his career, 3 different views about where algebra came from. The first one was, it must have come from the Greeks. But the Greeks were mean. They didn't want people down the line, centuries later, to steal this from them. So they kept it a secret. That was his first explanation. Then he said, algebra has grown in this country from whatever little there was in this continent, and he made a European thing for it. Well, there was no evidence for it. Finally he said, well, I invented algebra. Well, you can see that that discussion was taking place in the year 1500. But of course, now there is no doubt. Now there is no doubt about exactly how algebra came there. And in fact, it was the advent of algebra in Europe that did 2 very interesting things. First of all, it changed the meaning of mathematics. And as one great 20th century European scientist said, this is Hermann Weyl. Hermann Weyl said, India changed the definition of mathematics in Europe. In fact, somebody has made a survey of how frequently these different words are used. And they find that the use of the word mathematics began to overtake the use of the word geometry, or what earlier had been classified as mathematics, because they could not reject algebra. What's the point I'm trying to make? I'm trying to make the point that mathematics, there was a big contribution that India made at that time. And it lasted till 1500. And by 1500, 1600, 1400, 1500, the elementary rules of calculus were discovered in India, in Kerala. So till about 1500, 1600, science of an Indian kind was very strong in India. So, you can see that these things go up and down. After that, we must admit, it declined. It would be correct to say that after about 1600, or maybe even 1500, the new creative science being done in India declined. Why did it decline? Well, that's another big story. It involves politics, society, religion, etc., etc. But the advent of new mathematics in Europe led to a revolution there, starting with Newton, we can say, although there were some people earlier like Galileo and so on. And Newton, of course, was the big force which showed that the revolution was taking place right then. In 1700, there's a story about Aurangzeb. When the Europeans first came here, the Indians didn't want anything from them. They didn't think they had any new knowledge. They had nothing that they would sell them, or nothing that they would like to buy from the Europeans. He's supposed to have asked his advisor, who are these guys? And his advisor says, Your Majesty, don't worry about them. They come from a tiny little island which is smaller than your smallest Suba, he says. That was around 1700. But before he died, by 1707, they were becoming a menace. And he already began to see that they had things which he didn't have. There was some strength in the Europeans which he didn't have. So he begins to take his advisor to task, say, you said these guys are useless, but look at these new things that they have. So then India began to change. There was some force from the West, which we are not aware of. So you can say that our decline certainly started from then. And during the next few centuries, we must admit, unlikely as it is, that till about the 20th century, there's no great contribution that went from India. Now, let me conclude. I think I've already probably said too much. Is science for science sake important? Should we go ahead and keep doing science for science sake? Well, I would say it's absolutely necessary. Because if it's not necessary, if you don't do it, you do not know what you're going to miss. However, the word science for science sake, all those words, have to be carefully interpreted. I can't just say, I make some trivial calculation here, it is science. Don't tell me that it's useless. It's science for science sake. But the science for science sake which you suffer is not that kind of trivial new calculations or some new experiments or some new value I find, although it's going to be useful perhaps. It is where there is an idea which we had never dreamt of. And those ideas have usually come from people who think in their own ways and who are not afraid to go away from the value at that time which is accepted. And who are not afraid to live during years when people will say this is useless. Quite often, unfortunately, it's only after they've died that people have discovered that these ideas were great, and in fact they've caused this revolution. Science is there for science for its own sake is therefore necessary, but it is not sufficient. You can't say science for science sake and let's not do anything else. Science for science sake becomes useful to the common man and to mankind in general only when it begins to be applied also. Therefore, there is also technology there as a sort of word which includes, very inclusive, any use that may be made of that knowledge. Eventually it will have to be converted to technology. And the reason that Europe became so strong was that it combined science, like Newton's science, with technology, like James Watt and all these other people. And the combination turned out to be extraordinary. It was world-changing. We have to admit that. It changed the world. A nation which had been the wealthiest, India in around 1700 was wealthier than China, became a poor nation in the 19th century. We've still not gotten out of it yet. And one reason why I say all of this is that I think if we have the confidence, and the confidence of what happened in this country in an earlier period is actually an important one, If we have that confidence, if we have the passion, I'm sure we will do the science. The 20th century proved that Indians could do science as great as what was being done elsewhere, and Ramanujan is the outstanding example. And Ramanujan is an example which is very important, and I must particularly say this before an audience of teachers. Please remember that Ramanujan could not be admitted to any university in India. Why? He flunked his exams. He flunked his exams in English, and by the rules that prevailed then, and the rules that prevail even now in most cases, he was not qualified. But fortunately he had some friends who knew that he was doing some extraordinary mathematics which nobody else understood. They also didn't understand it. But that he had some kind of talent, many people saw. Some of his relatives, his friends, some of the officers he knew, they could see that this was an exceptional man. He couldn't get his degrees in India. So eventually this reaches manager of the Port Trust in Madras, an Englishman, and he looks at all of this and he says, okay, you should let me show it to somebody in England, see what they say. So they send it to people. The first man didn't think much of it, and the second man turned out to be Hardy. Hardy was dumbfounded because there were some results which were known and some results which nobody had even dreamed of. So he said, a man who can do this can't be dishonest. You can't invent all these new things. If you are dishonest, you can't cook them up. And whatever he could verify, he verified, and they turned out to be true. There were one or two which turned out to be not true as well. But he was so convinced about this man's unusual talent that he took the trouble to get him to England. You know, what Hardy did was almost as great as what Ramanujan did. This guy, poor Clark, he goes there to England, well, with all his Brahminical habits, and tells Hardy about what he can do, what are the things and so on. Hardy is always asking for the proof. Ramanujan can't give proofs, that's not in the Indian tradition. But anyway, he learns a little bit of it. And at the end of 2-3 years, he's got his bachelor's degree. And at the end of that, he's fellow of Trinity College. Now, I think most teachers here will know the prestige that belongs to being a fellow of Trinity College. It's about the best thing that can happen to an ambitious scientist. It's a treasured position in England by the English. So it is this Indian who comes here without a bachelor's degree. He gets his degree, he gets the fellowship of the Trinity College, and pretty soon thereafter he is nominated to the Royal Society and even elected. But unfortunately he had fallen sick by then. He came back to India and he could never go there to accept that fellowship legally or sign in that register which the Royal Society is so proud of, all these big names. Couldn't do it. So in the 20th century, this battle between, or this contest between Indic science and Western science had begun to yield results in India. Well, I hope the 21st century will be very different, and that we will once again emerge from our dark ages, which I say is from about 1500 to about 1800, 1900, say, 300 or 400 years. Europe had a dark age of 1400 years. We had a dark age of only 500 years at most. So it must give us confidence, and we must once again look at what we can do in the future. Science for science sake, science for passion, but technology also for passion. Anything you want to do, you choose the thing that you'll be passionate about. That's the best way. I am convinced that India does not lack talent. But India does lack, at least today, now in today's India, we lack the ability to manage talent, to recognize talent and to manage talent. That we can't do. Talented men are usually somewhat unusual, quirky, and they have their own preferences and so on. You have to learn to live with it. As long as it's not violence, how does it matter if a person is different?